right, let's get the variance of a geometric with parameter p. So to begin with, let's get the second moment, okay? And then we'll have to remember to come back in the end and use that inside-outside formula, okay? So the second moment is going to be the sum. Let's see, geometrics go from 1 to infinity, right? They can take on any strictly positive integer value. Find the second moment, so I'm going to square that value, multiply by the probability mass function. And so probability mass function, though, in this case is actually, I know it's to be 1 minus p raised to the k minus 1 times p. All right? Now I'm going to pull that p out, the summation, make it look a little bit better there. And got this. Now let's see, what can I do here? You know what? What if we note that all this stuff looks a lot like, all this stuff right in here looks a lot like the derivative of k times 1 minus p to the k, doesn't it? And then, of course, multiply by -1. In fact, that's exactly what that is. So I'm just going to replace that with this. So this is similar to the trick that we used when we derived the expected value. So negative d dp k 1 minus p to the k. All right. And now, what did we do last time? We actually pulled the derivative operator outside. I'll take the minus sign with it. But now this is okay. This is okay. It's not always okay to interchange the order of differentiation and summation if you have an infinite sum there, but I think it's going to be okay in this case. Take this will be negative p times d dp of the sum k equals 1 to infinity of k times 1 minus p to the k. Okay? Now, at this point, what you want to, if you want to get good at this stuff, start recognizing, if you can, what some of these summations look like. This looks a lot like the expected value of x, doesn't it? The expected value of a geometric, because it's the summation from 1 to infinity of k times 1 minus p to the k minus 1 and then times p, right? It's not the expected value of x, but it's pretty close to it. So what I'm going to do is to simplify this stuff, and this is a common trick, you just turn it into the thing that you are familiar with, right? And then compensate for it. So if I do that, it's k times 1 minus p to the k minus 1 times p. This will be the mean, but now, so I've got to compensate for doing that, otherwise I won't have equality there. So what if I multiply by 1 minus p over p, right? Good. Now, this stuff I can take out of the summation, right? I can pull that stuff out. You pull that out. Oops, not all the way out. I can't pull it outside the derivative because I'm differentiating with respect to p, but I'll put it basically there. I'm going to move up that way, okay? Here we go. So all that stuff down there is negative p times d dp of 1 minus p over p times that sum, right? K goes from 1 to infinity of k times 1 minus p to the k minus 1 times p. But like I said, this is the expected value of x for geometric, and we already worked all that out. It was 1 over p, right? So all this stuff is now negative p times d dp of 1 minus p over p squared. Okay, I could write that as negative p times d dp of 1 over p squared minus 1 over p, right? Now, I'll differentiate finally. That's going to be negative 2p to the negative 3, right? And then minus, if I take the derivative of this part, I've got my negative sign there. Derivative of p to the negative 1 is negative 1 times p to the negative 2. Right? Now, if I multiply through there, what do you get? You get 2p over p cubed minus minus minus. 3 minus is a minus. It's p over p squared, I think. So all of this turns out to be 2 over p squared minus p over p squared, or just 2 minus p over p squared. Whew. Now, finally, remember, we have to go back and use that inside-outside formula. We're not done. This is not the variance. This is just the second moment. So the variance of this geometric p is the expected value of x squared minus the expected value of x quantity squared. It's going to be 2 minus p over p squared minus, remember the expected value of x was 1 over p. I'm going to square that. So all this turns out to be 1 minus p over p squared. And so there we go. I hope you enjoyed that. Quick little example here. What if we want to know the standard deviation of the number of times that Marty must attempt to start the time machine until it starts for the first time? Well, so the standard deviation is just the square root of the variance. Okay, so I'm going to just take all this stuff up here, but with p equal to 0.1, my success probability. Okay, 1 minus 0.1 over 0.1 squared. That's going to be something like 0.9 over 0.1 squared. I get 9.4868. Okay.